Let us discuss then subsets of the Lebesgue spaces. And just to give you an idea, the relevance of having a dense subset. So, for instance, you want to prove a certain property, let's say an equation or an inequality involving Lebesgue functions. If you know a dense subset that has more properties, for instance, continuity or differentiability, the first step is to prove that property, let's say that inequality, on the dense subset. And then you approximate a given Lebesgue function by an element of the dense subset for which you can easily verify the inequality, and then pass to the limit to deduce the inequality for all Lebesgue functions, provided that, of course, the expressions or the terms on both sides of the inequality are stable with respect to the Lebesgue norm. And that is sometimes called density argument. So for this lecture, we consider a specific type of domain for the Lebesgue spaces. And later we will discuss a specific type of measure as well. In particular, we will consider the so-called locally compact normal topological spaces. So a topological space X is called locally compact if for any point X in the space, one can find, so let's say you have a point X, one can find an open set that contains this point, okay, and then there's a compact set containing this open set. So in other words, space is locally compact if at each point of the space you can find a compact set that contains an open neighborhood of the point. And when is it normal? It is said to be, or it's called normal if your topological space is Hausdorff. So again, Hausdorff means that if you have 2 points, then you can find 2 neighborhoods that separates these 2 points. So that is a Hausdorff space. Normal means that all singletons are closed. Okay. So LCN here will be an abbreviation for a locally compact normal space. And you can think of, let's say, any open set in Rn or the whole space Rn itself. So take note that Rn is not compact, neither an open set in Rn, but they are locally compact normal spaces. So later, in order to prove our main theorem in this lecture, we need the following version of the Urison's lemma. For locally compact normal spaces. So this is an extension of your usual Urison's lemma. So let me state the lemma. So suppose I have a locally compact topological space X, K a compact subset, and an open set U, such that K is contained in U, and of course U is a subset of X. Then it is possible to find, or there exists function f that has a compact support in X, And the support lies in U. F restricted to the compact set is identically constant and it's equal to 1. And the range is between 0 to 1. So you have a non-negative function between 0 to 1 that is 1 on the compact set, and the support is in U. So to illustrate that, we have this function f. Let's say our space x is this real line. So this is our space x. You can think of the real line. So that function f is 1 on this compact set. So imagine a compact interval. And the support is the subset of the open set U. Think of an open interval, for instance. And the function is between 0 to 1, or it has values between 0 to 1. So the maximum would be in this function k. So you can, this compact set k. As I said, you can think of this as a plateau function wherein you have a flat region on the compact set k. So that is our function f in Urysohn's lemma. I will not provide the details of the proof. I'll just give you here the main idea, or main ideas. So you apply the so-called Alexandrov one-point compactification of your topological space that is only locally compact. And of course, you apply the usual Urysohn lemma for normal spaces, normal topological spaces. The details are, of course, in the course notes. So Urysohn's lemma is the same as this. We have the same conclusion as this one here. But that lemma is only applicable for normal spaces. Okay. For compact normal spaces, to be precise. And let us correct that one. Normal and compact spaces. Okay, so I will just give you a brief introduction, or just an illustration for the Alexandrov one-point compactification in the case of the real numbers. So we know that the topological space R, of course, under its usual topology, is not compact, but we can add a compact, one point that will make it compact. And the idea is to consider this point, and you can think of this as the point positive and negative infinity, collapse into a single one in this way. So S1 here is the unit circle. That is the boundary of the unit circle. And what you do is, if you have, let's say, a point on the real line, you take the line passing through this point, and then the apex, or the top of the unit circle, and the intersection would be that correspondence. So take note, given a point on the line, on the real line, there is exactly one point on the unit circle, and vice versa. any point on the unit circle except on the top, this one, is mapped to a point in R. So by adding this point here, you will have a one-to-one correspondence between the set of points in or on the unit circle and the point at infinity. And if you take the correspondence, okay, if you map this, let's say, to the point infinity, the point at infinity, then you can make R combined with that point to be compact. So the one-point compactification of R here is isomorphic to the unit circle. And if you want more details on the one-point compactification and the associated topology, you can, for instance, look at the book of Yoshida, Functional Analysis. Okay, so that's Urysohn's lemma for locally compact normal spaces. It's basically the same as the conclusion of Urysohn's lemma for normal and compact spaces. So the idea is to apply or to add one point that will make the locally compact normal space into a compact one. With this, we can now prove the following density theorem. Let us state the assumptions. So suppose X is a locally compact normal space, Y a Banach space, and we have a measure on the Borel sets of X. And that is regular. And by that, we mean the following. So for any Borel set, say A and X, the measure of A is the same as the supremum of all measures of compact sets contained in A. And this is inner regularity. And similarly for outer regularity, we have that the infimum of measures now of open sets containing A should be the same as the measure of A. This would be outer regularity. So an inner and outer regular measure on the Borel sets is called a regular Borel measure. Then the set of all continuous functions with a compact support in X with values in Y is dense in LP. So this is your measure space, and then the values is in Y. Of course, for P that is finite. When P is equal to infinity, this is not true in general. Okay, so let's look at the proof. So let us start first with a Borel set having a finite measure. And at this point, let us first consider y equals r. Now, given a positive epsilon by regularity of your measure mu, there exists a compact K and an open set O that satisfy these inclusions. So K subset of A and A subset of O, such that the measure of O minus K would be less than epsilon. Or let's say, let us rescale that one, epsilon over 2 raised to the power p. And you can easily see this from these properties here. Okay, just simply apply the definition of the supremum and the infimum. And of course, here K has a finite measure due to monotonicity, since K is a subset of A. Therefore, mu of K is finite. Hence, the difference, the measure of the set difference is just the difference of the measures. So based on this, we now apply the Urison's lemma. For the locally compact normal space X, so that we have, so there exists a function f. Let us denote this by f sub a, okay, corresponding the set A that has compact support in X with values in R, wherein we have, okay, the support of f of A is contained in O, f sub A restricted to K is identically 1, and the image is a subset of 0 to 1. The closed interval 0 to 1. So you can apply this lemma here with U, of course, replaced by O. And you have this equation, or you have these properties here. From this, we can now estimate, let's say, the LP norm of this function and the indicator function. So the indicator function, or the characteristic function, 1 sub A. So it is 1 if it is in A, and it is 0 otherwise. Okay. Since the support of f sub A enhance the support of A lies in O, we can restrict the integral in O. Furthermore, f sub A and the indicator function are both 1 inside K. So we can subtract that as well, because this difference will be 0, since both functions are equal to 1 in K. So obviously, This is less than or equal to, so you apply the triangle inequality. And since S sub A, the magnitude or the absolute value is less than 1, similarly for the characteristic function, this is less than 2. So we can now apply, let's say, this estimate. So 2 raised to p. Since this is constant, so you have 2 raised to p times the measure of the set difference. And if you apply this inequality here, this is less than epsilon raised to p, raising to the power 1 over p. We then obtain that the LP norm of this plateau function f sub a, the one obtained from Urysohn's lemma, and this characteristic function is less than epsilon. So that's the first step. So we were able to find a plateau function that is close to the characteristic function of a set having a finite measure. Now, to prove density, okay, so let us take an arbitrary function in the Lebesgue space. And an arbitrary positive epsilon. Now, take note that from the construction of the Lebesgue-Bochner integral, simple functions are dense in this space. So if you want to look at the specific details, you may consult the book of Alt, for instance. This implies that there exists a simple function, let's call that phi epsilon, such that the distance between f and this simple function is less than epsilon over 2. Okay, so let us write a simple function in its this way. So let's say I should correct this into y. So phi epsilon is equal to the sum, let's say, of some y sub I, 1a sub I, where y sub I is in the Banach space capital Y. A sub i's are Borel sets having a finite measure. Of course, this should be A sub I. It's basically the definition of the simple function. Here we emphasize the number of terms in terms of the epsilon. So the smaller the epsilon, you might need more values in your simple function. Okay, so let us define, let's say, or set m sub epsilon to be the sum of the norms of the values of your simple function. Now, if we apply the first case or the first discussion that we have in the proof, this one, and rescaling epsilon. So for each I, there exists a plateau function f sub a sub I with a compact support, and this has values in, let's say, y, in R, okay, such that, okay, the distance between your plateau function with this characteristic function is less than epsilon over 2 divided by m epsilon. Here, without loss of generality, we assume that none of the y sub i's are 0. Otherwise, your simple function would be 0, and f would be close to 0. Okay. Or you can just adjust the denominator in the case when your simple function is 0 by this one, plus 1, so that the denominator will not be equal to 0. Now, if I take, let's say, I define f sub epsilon to be the same as or similar to the simple function, but what I do is I replace the characteristic functions by the plateau functions f sub a sub I. And this is clearly continuous, since the sum of continuous or a linear combination of continuous functions is again continuous, and it has compact support since the support lies in the union of the supports of your plateau function. And take note that a finite union of compact sets is again compact. Okay, so if we apply the triangle inequality, estimating the distance between this sum of plateau functions with the simple function constructed above, from the definitions of f sub epsilon and I phi sub epsilon, this is less than or equal to the sum of this distance. So the distance between the plateau functions and the characteristic functions, and then the norm of y sub i's. Okay, so applying this estimate here, this is less than or equal to the following sum. So this is epsilon over 2 m epsilon plus 1. And since this is a constant, we can pull out later. And from the definition of m epsilon, okay, this one, this quantity is certainly less than epsilon over 2. Okay, let us highlight what we have established. So that's one inequality. And this is the other inequality. So by simply applying the triangle inequality, you obtain from these two that the distance between f and f sub epsilon is less than epsilon. And that ends the proof. So an arbitrary f can be made sufficiently close to a given function in this space. Hence, the density of that, or the density of continuous functions having compact support in X with respect to the Lebesgue space. So let's have a recap of the proof. So the main idea is first you consider characteristic functions on Borel sets having finite measure. Okay, choose or take a continuous function with compact support that are close to these characteristic functions. And these are the plateau functions f sub a provided by Urison's lemma. So once you have done that in the case of characteristic functions, you can apply the density of simple functions. And for each characteristic function on the simple function, you apply the previous case. And you obtain a function that is continuous and has compact support in X that is close enough to your given function f. So yeah, that's the proof of this theorem. And in fact, we can extend this further. So we have the following corollary. So with the assumptions as in the previous theorem, of course, if D is dense in Y, and or let's say then the set consider the following tensor product. Well, this is basically what the product of functions f d. So f here is a function with compact support in X with real values, of course. D is in capital D. Then if you take the linear span of this tensor product, this is dense in the Lebesgue space LPX, Borel sets, and then your regular Borel measure mu with values in Y. Okay. Take note that this span is obviously contained in the set of continuous functions having compact support in Y. So by span, we mean here a finite linear combinations of elements in this tensor product. So even I found a smaller dense subset of the Lebesgue space LP. So let us again emphasize that this is the case when P is finite. So for a quick proof, given let's say epsilon greater than 0. So following the proof as before, there exists, let's say, an epsilon. Let us first write the LP function. Say f. So there exists, let's say, an f sub epsilon, f sub I, y sub I. such that, so this is the proof a while ago. This belongs to, of course, this belongs to the linear span, okay, of this tensor product, such that f, the distance between f and this f sub epsilon is less than epsilon over 2 by, of course, the previous theorem, and up to renaming the plateau function by, let's say, f sub I. And now you see we replace these y sub i's. Of course, y sub I is in capital Y. And f sub i's are in this space, C naught x. So we replace each y sub I by a d sub I by the density of d and y in such a way that the distance between y sub I and d sub I can be made small enough. And in this case, we take the following: epsilon over, let's say, 2n epsilon, f sub I. We take the L infinity norm, which is finite due to the fact that f sub I is continuous and has a complex of 4. Well, if this is 0, then we just add 1. Then it follows easily that g sub epsilon, defined in this way. So following the definition of f sub epsilon, but now replacing y sub I by d sub I, this is clearly in the span of this space. And now I see the mistake with the argument. It should be y. Okay. If this is a g sub epsilon, then estimating the difference between f sub epsilon and g sub epsilon by the triangle inequality. This is simply less than or equal to this one. So you apply the definitions of f sub epsilon and g sub epsilon. And following this estimate here, you now have the following upper bound. Okay. And this is, well, less than or equal to epsilon over 2. And you can verify this by a simple algebra. Hence, applying the triangle inequality once again, you have this inequality establishing the density of the linear span of this tensor product in the Lebesgue space LP. Okay, so that's it. This is the main idea. You follow, or you just continue the proof of the previous theorem, and you replace each y sub I by an element d sub I in the dense set. An immediate corollary, of course, is that if omega is open, which is obviously locally compact normal topological space taken as a subspace of Rn, then C naught omega let's say B is dense in Y. Here we consider of course, the Lebesgue measure space. Then, as before, the span of this tensor product is dense in LP omega Y. And this LP omega Y is what? If you want to be precise, this is B of omega. And you have the Borel sets in omega with respect to the n-dimensional Lebesgue-Borel measure, and with values in Y. Therefore, LP functions, let's say here, can be approximated as a linear span of linear combinations with functions with real-valued functions having compact support in omega, and the coefficient vector is in the dense set D, which is a subset of Y. Okay, so that's a dense subset of LP. In the next lecture, we will consider the case when omega is Rn and Y is in Rn, and we even look for a smaller dense subset. In fact, we can take test functions to be dense in LP omega with values in R or Rn. This will be provided in the next lecture.